welcome back to another installment of A Night at the Museum. Tonight's lecture is going to be about the age of the dinosaurs and the hothouse climates that allowed the giant reptiles that we call the dinosaurs to exist, the terrible lizards. I want to introduce a very wide-ranging and collaborative research project. I haven't been directly involved in it, but it's been an important part of how we've been able to understand the carbon cycle on geologic timescales. It's called GeoCarb, and it's a model-based estimate that makes predictions about how high CO2 levels have been through time. And so what you're seeing here is the output of this model, which factors in plate tectonics and volcanism. It's been compared with paleoclimate proxy records like the ones that we talked about in previous lectures to show that through time, early, say in the Cambrian period, going all the way back 600 million years ago to the pre-Cambrian period, CO2 levels were higher. And then as we move into what we were talking about last time, the Carboniferous, where there's an imbalance on land because plants are taking up more CO2 and storing it in the rocks, and they're releasing back out because there aren't bacteria to digest woody tissue. And so over millions of years, CO2 levels start to decrease. And we see for the first time in a long time, the presence of large ice sheets on land. Now this is a combination of factors. There's really two important ingredients to having ice sheets on land. Number one, you have to have a continent near the poles. You just have to have somewhere to put the ice, and that should be near the poles. Number two, from this graph, from other paleoclimate and geologic evidence, we know that you also have to have relatively low CO2 levels. So CO2 levels in the atmosphere that are as low as they are now, or maybe even lower. And those two ingredients seem to be really critical for having large ice sheets. And today we do have large ice sheets. There's a large ice sheet on the Antarctic continent. There's also a relatively large ice sheet on the Greenland. Now, if you move forward through time, Carboniferous, the Permian is a climate that's not in many ways dissimilar to today. The supercontinent Pangaea existed at the time. All the world's continental mass was unified in this one large continent. So that was a big difference. But there were parts of that continent that stretched far enough south to host ice sheets. And CO2 levels were similar to what they are now. And the global average temperatures were also roughly similar to what they are now. But as we talked about, things ended badly for the creatures that were alive in the Permian. It led to one of the worst, maybe the worst mass extinction event in Earth's history. And it was driven largely by CO2 emissions that triggered global warming, that triggered a whole host of biogeochemical feedbacks that made the planet less hospitable for the life forms that existed at the time. But to quote from Jurassic Park, life finds a way, life found a way, and rebounded into the Triassic, the Cretaceous. And what we're seeing in this geocarb reconstruction is that during this period of time, after the Permian, into the Triassic, and beyond, this whole age of dinosaurs for several hundreds of millions of years, CO2 levels were much higher than they are now. We're not even at 500 ppm, parts per million. We're somewhere in the low 400s right now. We'll probably reach 500 in another couple of decades at the rate that we're going. But the Triassic and the warm periods that followed the Permian extinction were in the thousands of ppm CO2. And importantly, there's no evidence of large ice sheets on land. And this is obviously very relevant for today, because if we enter a CO2 world, a hothouse world with high CO2 levels analogous to the time of the dinosaurs, we might not be able to have ice sheets, and that would trigger catastrophic sea level rise and disruptions to global weather patterns and ocean currents, unlike anything that we've seen. I mean, what we've seen now with climate impacts is not even the tip of the tipping point if we enter one of these hothouse climates, and if we're unlucky enough to be around to see what happens. It's not an experiment I want to be part of. I'm hoping we will not run that experiment on this planet. We'll do it with our models. That'll be good enough, and then hopefully walk away knowing that we averted a world that we would hardly even recognize. During this period, this hothouse world of the dinosaurs, which are no longer around for the most part, we have a number of environmental conditions that lead to the formation of today's hydrocarbon resources in the form of oil and gas. So what I want you to do is I want you to look at this map here, and I've put some markers in it that I want you to follow. These are paleogeographic reconstructions. You can see there's a continent far enough south to have ice sheets, but there are no ice sheets on that continent. This is a hothouse world, much warmer than today. And you can hopefully recognize most of the continents, the precursors to the continents that we have now. And what I want you to do is just pick one of these markers and follow it as we step through time. Because these are all shallow inland seas or continental margins where organic material builds up and gives us our oil and gas deposits. Keep following them, and boom, look at that. These are 6 of the biggest oil reserves in the world that you've been following. Let's walk through that again. Start back 90 million years ago. Pick a dot. It's either going to be a shallow inland sea or a continental margin. And the reason why these environments are favorable for hydrocarbons building up is because you have lots of terrestrial biomass in the form of plants, and they're planty bits. When they die, they get washed into streams, they get washed into rivers, they get washed into deltas, they get washed into the ocean or the shallow seas and the continental margins, and they build up, law of superposition, layer upon layer upon layer, and under enormous heat and pressure and time, those organic rich deposits become the hydrocarbons that we're using today, oil and gas. So watch it again. Pick your favorite dots. Wait for it. Boom. Venezuela, Saudi Arabia, Iran, Russia, Libya, Canadian. These are huge, huge. Canada. Did I say Canadian? Canada. We'll fix it in post. It's fine. Huge oil deposits that we're still pumping and relying on today for our global economy. And it's an artifact, it's a function, an accident of geology that some countries just happen to be sitting on top of these hydrocarbon reserves, which 200 years ago had no value. It wouldn't be until the 1900s that we started to develop the technology to extract this high density, high energy density liquid hydrocarbon that we call oil, and not until another few decades that we could really make use of the hydrocarbons that we call natural gas. And it just happens that some of these countries are positioned on top of these deposits, which were buried in the earth for millions of years. And to really understand our role in disrupting the global carbon cycle, we need to think about the global carbon cycle on 2 different timescales. Long-term processes that affect the global carbon cycle, so million-year timescales, as well as the short-term processes. So let's start with the long-term processes. On the long-term processes, we're going to walk through from left to right. You have chemical weathering, so they're chemical reactions that require liquid water. We talked about this in the lectures about Venus and the Goldilocks zone. Chemical reactions that require liquid water and dissolve CO2 in that water that remove carbon dioxide from the atmosphere and store it in a solid form in the rocks. There's also erosion that can release organic carbon from weathering of sedimentary rocks. And we have examples of this all over town. If you walk the Gorge Trail, you walk Fall Creek, you watch Cascadilla, you will see those beautiful characteristic cliffs in the Ithaca gorges. Those are rich in organic material. The streams that have cut in to form those beautiful canyons that we walk through are ancient marine deposits, and they're full of ancient carbon from life forms that were once swimming in the seas, and when they died, were buried in those sedimentary rocks. Now, the erosion that's happening in those streams is causing some of that carbon to be released back into the atmosphere. But these are long timescales, hundreds of thousands, millions of years. Now, the organic material that makes it into the oceans and the organic material from the oceans themselves gets buried in the ocean floor and locked out of the atmosphere, out of the global climate carbon cycle for hundreds of thousands or millions of years. There's also the burial of calcium carbonate, which again, on the ocean floor, we looked at this in the context of some of the sediments in the lecture on the Permian reconstructions that used foraminifera. That's an example of a marine sediment that has a calcium carbonate skeleton. And when it died, fell to the bottom of the ocean floor, its carbon from the CaCO3 was locked down to the carbon cycle. Now we get to the mid-ocean ridges. This is a major source of CO2. Bubbles into the oceans, and eventually some of it will outgas into the atmosphere. An important source, a natural source of carbon dioxide, but it's tiny compared to industrial emissions. I want to emphasize that. Even though in the natural system, there's a lot of CO2 being released, compared to human activities, it's small. Now, on the other side, we have an area where one plate is colliding with another plate. This is analogous to what's happening in the western part of the North American continent. So you can think of these like the Cascade mountain ranges, for example. So you have a subduction zone, and while the ocean floor is subducting beneath the continental plate, there's off-gassing, there's release from metamorphism and diagenesis, so that's putting CO2 and methane back into the atmosphere. And there's also some carbon that's going deeper and deeper into the earth. Eventually, a little bit of that will come back out from volcanic emissions of CO2. But these are all timescales. We're talking about millions, tens of millions, hundreds of millions. This is the long carbon cycle, the long timescales of the carbon cycle. Prefer to look at this conceptually. Made this concept map for you all. There's an interaction now with the short timescales. The ocean, atmosphere, the living organisms, biota, and the soils. So let's look at a little more depth at the short timescales associated with the carbon cycle. There's four big ones that I want you to focus on, the four reservoirs that we want to focus on. There's the ocean reservoir, where there's a lot of dissolved carbon. There's the atmosphere, where there is carbon dioxide floating around all of us right now. And compared to the oceans, the mass of CO2 that's in the atmosphere is relatively small, but it's important, obviously, for the greenhouse effect. There's quite a lot of carbon stored in soils, which are just the bits of plants that are slowly being digested by bacteria. The more slowly the bacteria digest the soils, the more accumulation of soil organic material you get. So in high latitude areas here and farther north, you have colder climates, and those colder climates have very slow microbial digestion rates of the soil. And so lots of soil can accumulate, or peat can accumulate as well. Peat bogs can accumulate a lot of organic carbon. In more tropical environments, and in environments probably analogous to the ones that the dinosaurs may have lived in, the microbes are very happy throughout the year. They don't have they don't have an off season. They're always just chewing up that carbon. Yum, 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 yum. And so there's very little topsoil in warmer and especially warm, humid regions. And then you have the biosphere itself, the carbon that's stored in all the living organisms throughout the entire world, on land and in the oceans. And between each of these reservoirs, places where carbon is stored, you have processes that are moving carbon around. So microbial respiration takes soil carbon and puts it into the atmosphere, like we just discussed. Now, when there's this atmospheric carbon available, terrestrial photosynthesis can take that CO2 from the atmosphere and store it in the form of either tissue in plants or in the form of marine photosynthesis. The carbon goes from the atmosphere into the ocean, and it's the dissolved CO2 that algae has at their disposal to do photosynthesis, but it still enters the biosphere. Once it's in the biosphere, respiration, we're all doing it. We're releasing CO2. Every time we breathe out, we're doing respiration. We're putting CO2 back into the reservoir of the atmosphere. There's respiration, there's respiration from the marine organisms as well. There's also direct gas exchange. So if I were to close up this bottle of kombucha, shake it up a little bit, know if you could hear that. There's a slight release of CO2. There's an equilibration of the CO2 that was dissolved inside the bottle of kombucha, and it's released in the atmosphere. There's a lot more dissolved CO2 in the bottom of the oceans, and when the bottom ocean waters are exposed to the atmosphere, they tend to degas. It's analogous to like opening a can of soda or opening a delicious bottle of kombucha. There's no biology involved, though, and this happens almost instantaneously. And we've benefited from this tremendously because since the Industrial Revolution, about half of the CO2 that we've released in the atmosphere has been absorbed just directly by the oceans. Now, it's made the oceans more acidic. So even if you're not concerned about climate change, the oceans are becoming more acidic. And that is affecting microorganisms and invertebrates in some areas already. And it's simply because when the atmosphere has higher CO2 in it, the oceans take up about half that. And when CO2 dissolves, it forms a weak acid. And that's causing ocean acidification that we're already seeing today. Again, there's marine respiration. So this includes all the bacterial activity, but also, like whales and sharks and fishes that are doing respiration. They're eating other organisms, or they're eating phytoplankton, or they're eating algae, and they are releasing CO2 back into the ocean. And then finally, off to the left here, a process that's important, I've talked about for removing carbon from the land surface into the oceans and also contributes to the hydrocarbon resources we have, is river transport. So organic material gets washed from the soils into the streams, into the rivers, into the oceans, where it can either form the ocean carbon reservoir, be part of the ocean carbon reservoir, or be deposited on the ocean floor and removed and locked down to the carbon cycle. What's important to understand is that what we're doing is creating a portal, like a portal through time, where our current economy depends on access to hydrocarbon reservoirs, carbon that's been stored in the rocks for millions or hundreds of millions of years, and releasing it very quickly on geologic timescales, almost instantaneously on geologic timescales, into the atmosphere. We've created, with our modern industrial system, a link to the past that lets us just burn and extract and use energy that's been locked down to the climate system, carbon that's been locked down to the climate system for millions of years. So human activities are disrupting all of these carbon reservoirs. You see the influence of human activities from burning fossil fuels in every single one of these reservoirs and every single one of these fluxes. The reason why we wanted to do it in this part of the museum is because, to my mind, what we're doing now with fossil fuels is kind of analogous to the old Godzilla movies, where we've like dug too deep and we've awakened something from the past. And what we've awakened from the past are these the potential for these much hotter climates, which have a lot of carbon dioxide in the atmosphere, and which can push us past some important tipping points, where if the world becomes warmer and warmer, including at the high latitudes, well, what's going to happen to the soil carbon? Well, the microbes are going to have more time to chew up all that yummy soil carbon. The high latitudes are going to start to look more and more like the tropics. That means less topsoil. That means more CO2 in the atmosphere. That makes it harder and harder to lock carbon out of the atmosphere and keep it stored on land or keep it stored in the oceans. When we think about climate change, I think a useful way of framing it is in this almost science fiction-like context, where we've dug into the earth and we have unleashed atmospheres and the potential for climates that no human being alive today, no human being that has ever lived would have experienced. That's what we're toying with when we think about the tipping points that we might be approaching very quickly right now. Of course, in the second half of this lecture series, we're going to get at the solutions. But if it makes you uncomfortable, good. It should make you feel a little bit uneasy that we are toying with processes that could unleash climates that spell out our demise. And I hope that you can sit with that feeling, not be paralyzed by it, but use it to do important work that needs to be done by your generation, by my generation, by future generations to stabilize the climate system and avert some of those potentially catastrophic outcomes that as far as we can tell right now, are not unlikely to occur if we stay on our current trajectory. Isn't that right? Got nothing to say. All right. Thank you. I almost forgot that it was behind me this whole time. There were a few times I was like looking around and I'd see one of them, I'm like, all right, there's a dinosaur like right behind me.